Okay, we're picking up in this part 2 of the matrix equations of motion, and this is obviously at the element level. We're picking up from the previous lecture. So I've already written down the equations that we obtained in part 1 of this lecture, and I'm going to label those as equation 1. Okay, so just as a reminder, that first equation is m sub s, which is, as we'll show in a minute, is a submatrix, an 8x8 submatrix, times the acceleration vector in the u1 direction plus the integral of the following: the partial of the interpolation function n with respect to x1 times sigma 1,1 plus the partial of the interpolation function n with respect to x2 times sigma 1,2 plus the partial of the interpolation functions with respect to x3 times sigma 1,3. So the strategy here that we want to employ is we would like to get these equations to all be functions of displacement or displacement derivatives. So what we're going to do in this to carry this forward is we're going to go ahead and use we're going to assume an orthotropic material and use Hooke's law for a linear elastic material to define this. Okay, so let me write that down. Okay, so here we go. We're going to go ahead and use Hooke's law for a linear elastic material. And in this case, we're going to say it's orthotropic. And what that means is that it can be uniquely defined by 9 elastic coefficients. Okay, and let me remind you what that looks like. Again, this is just for the sake of completion. I don't want you to feel like you haven't maybe seen this in a while and you're lost. So here's our stress vector: sigma 1,1, sigma 2,2, sigma 3,3, sigma 1,2, sigma 1,3, sigma 2,3. That's how I prefer to order my stress vector. There are alternate orderings, but we're going to use that pretty much exclusively in this class. Okay, and then this is our stiffness matrix C, and so in an orthotropic material, we'll have C11, C12, C13. It's symmetric, so this is also C12, C22, C23, C13, C23, and C33. And then I will write down here C44, C55, and then C66. Okay, and then these are all zeros. Zeros up here in the same fashion. Okay, and then multiplied by our strain vector, which is epsilon 1,1, epsilon 2,2, epsilon 3,3, 2 times epsilon 1,2, right? It's the engineering shear strain. 2 times epsilon 1,3, and then 2 times epsilon 2,3, right? So that's Hooke's law in matrix form for an orthotropic material. We'll call that equation 2. So now proceeding down, I'm not going to continue to write all 3 sets of equations. I'm just going to look at that first set of equations and work through that, and then I'll just write the others just down by analogy, okay? So I'll just say the integral in the first set of equations in equations 1 can be written using equation 2 as follows. Okay, we'll just say that the integral over the volume, so I'm going to write that integral down first, of this quantity n partial with respect to x1 times sigma 1,1 plus n partial with respect to x2 times sigma 1,2 plus n partial with respect to x3 times sigma 1,3 dv. Right, that's the term that is that first integral of equation 1. And what does that look like if I go ahead and use Hooke's law? Well, that looks like integral over the volume. Okay, it doesn't change the interpolation functions. That's the same. Okay. What it does do, though, is now I have to take that first equation and see that it gives me C11 times epsilon 1,1 plus C12 times epsilon 22 plus C13 times epsilon 33, right? And then I continue on, plus there's n partial with respect to x2, and now I go up and I look and see that that looks like 2 times C44 times epsilon 1, 2, and then plus interpolation function with respect to x3, 2 times C55 times epsilon 1, 3, right? So that's the substitution all over dv. Let's call that equation 3. Okay? What do we need to do now? Well, remember our goal, our strategy in all this is we want to take and get this integral so that it really is only in terms of the nodal displacements. So we still haven't got to displacements yet. We went from stresses to strains, and now we want to employ the strain-displacement relations in equation 3 to get us to those displacements, okay? So that's the next step. So employ the strain-displacement relations for small strain to get the following. Okay, I'm not going to write out that horrible integral again. I'm just going to say that's the integral of the quantity that's inside from above, okay, is going to be equal to, and I'll go below and so I can have room to write, integral of the volume. Okay, that first term doesn't change. That's just n, partial of n with respect to x1. And then inside this parenthesis, C11 doesn't change. Strain displacement relation of epsilon 1, 1, well, that's u1 comma 1, right, plus C12 times u2 comma 2 plus C13 times u3 comma 3, right? That's epsilon 1, 1, epsilon 2, 2, epsilon 3, 3, okay? Plus, remember the strain displacement relations is 1/2 epsilon ij is equal to 1/2 ui comma j plus uj comma I. So I have a 1/2 now times 2 in this equation that cancel out. And so I'm left with the partial of n with respect to x2 times C44. And then this quantity is u1 comma 2 plus u2 comma 1. And then I have a similar term here, plus n comma 3 C55 u1 comma 3 plus u3 comma 1 dv, okay? And we're going to call that equation 4. It's getting kind of long there. Okay, hopefully that's straightforward. Okay, so what's the next strategy? So we now have this equation written in terms of interpolation functions and displacements. Now what we want to do is we want to introduce the displacement approximation. Okay, so let's do that. Let's say now introduce the displacement approximation. Okay, and remember what that displacement approximation said. It said that ui star, the approximate displacement of u in the I direction, is going to be a function of both x and t, right? And that's going to be equal to the interpolation function n, which is only a function of x in this case, transpose times ui of t, right, where these are the nodal displacements as a function of time. Okay, so we'll call that equation 5. Okay, so that's the displacement approximation that we want to introduce. Okay, so using equation 5 and 4, okay, I'm going to do the same thing. I'm going to say this is the integral of this horrific quantity that I don't want to write down. Integral of dv is going to be equal to, okay, now I'm going to say integral over the volume. I'm going to have several lines, okay, so I'm just going to write this one giant bracket. Okay, so what's this first term look like? Well, first term is partial of n with respect to x1. That hasn't changed. And inside there, we have C11. Now, the approximation for U1 is just going to be n transpose times U1 of the nodal vectors. And then the partial doesn't play on the nodal vectors because those are only time dependent. It plays only on the interpolation functions. So this looks like n transpose comma 1, right, times U1. Okay, and I'm going to drop the t just for convenience. Okay, know that u can be dependent on time. Okay, next term looks like the exact same. So C12 now times n transpose partial with respect to x2 times UE2 plus C13. Hopefully you see a pattern now. Transpose partial with respect to x3 U3. Okay, so hopefully that's straightforward. We'll close the parenthesis there, and then we'll say there's the next term plus let's see, this term here, that partial of the interpolation function with respect to x2. Okay, partial n with respect to x2, and then there's a C44 that remains. And now let's think about what this looks like. Well, this is U1, right? U1 is, so that's going to decide which nodal coordinates I use, but the partial is on 2, right? So what we end up with is n transpose partial with respect to x2 times UE1. Okay, and then we flop those indexes. N transpose with respect to x1 times the nodal displacements U2, and I need to make that a curly bracket. Okay, parentheses will close. Now let's do the same thing with that final term. There's partial of n with respect to x3 times C55. Now the same thing. This term looks like n transpose partial with respect now to x3, still multiplied by the U1 nodal displacements. And then the next term, partial of n transpose with respect to x1. And now instead of the 2, this becomes 3. Okay. And thus we've completed it. Okay, dv. Let's call that equation 6. Okay. So I'm just showing you this one example for that first integral of equations 1. You're going to go ahead and perform this same procedure for the other integrals in equation 1. So those in the second and third lines. Okay. So that's the next step that I'm not going to write all down because I think it's straightforward now. So I'll just say perform the same procedure for the other two equations in equation 1. Okay. Okay, so what we have now is we have it's a little bit fractured. We have U1, the nodal displacements. We have U2, the nodal displacements, and U3, the nodal displacements. Remember, we're looking at, in this case, a 3D element, so that there are 8 nodes. So U1 is a 8-component vector. U2 is an 8-component vector. U3 is an 8-component vector. Okay, so what we'd like to be able to do is to write all of this in terms of a single set of matrix equations. So how do we do that? Well, we're gonna define the nodal displacement vector as follows, and the force vector, let's say. Okay, we're going to say that the nodal displacement, which can be a function of time, and I'll put E for element. Now you'll notice I don't have a subscript on it. Okay, that's going to be equal to the following vector. Okay, it's a vector. The first 8 components are UE1 as a function of t. The second 8 components are UE2 as a function of t. And the third 8 components, so there's 24 now. It'd be U3E as a function of t. And we'll close that up. Okay? So that's my displacement vector, my force vector, which also could be a function of time. I'm not going to subscript this anymore. I'm going to create a similar vector, but now this is going to be F1, which could be a function of time. The second 8 components is going to be F2 as a function of time. And the third set of 8 components will be F3 as a function of time. Okay? Let's call that equation 7. Okay, so what you can see if you look at equation 6 is that I'm going to have to group these in particular ways, and when you do that, you end up forming matrices that are square matrices that are 24 by 24, but really comprised of sub-block matrices that are 8 by 8. So I'll define what those are in just a minute. But if you follow equation 7 and then just put the equations in matrix form, this allows the element matrix equations of motion to be given by the following, where we have M. I'm going to put an E for remind you it's part of the element. ME, and we did this in the last lecture, but it's this term is U double dot, which could be a function of time, right? And I'm going to put an E back there to remind you it's element nodal accelerations, plus the stiffness matrix K sub E, right, times what we just defined, which is U of t at the element level, okay? And that's going to be equal to F of t. Maybe for consistency, I should put E's on that just to remind you, okay? Okay, let's call that equation 8. So here you have the element equations of motion. Let me define what these matrices look like for you. So it will just say here where the following is true, where the term ME, this is the mass matrix of the element, is equal to the following. Remember I said it was comprised of 8 by 8 submatrices, and the diagonal submatrices are the MS terms that you had from equation 1. And then I'm going to put zeros here just to remind you that it's not actually 0, but they're block matrices of zeros. Okay? And I encourage you to go and convince yourself of this. It's just an algebraic exercise to do it, but it's sort of tedious to do just in a lecture form because there's a lot of terms you have to keep track of. Okay, so we'll call this equation 9. And what can I say? This zero matrix, this is an 8 by 8 submatrix of zeros. Right, and this term, this is also an 8 by 8 matrix, which we defined in the previous lecture and said that, right, M sub S is equal to the integral over the volume of rho times N transpose dV, right? That's how we define that. And so what you can see about the mass matrix as it's derived is that it's block diagonal, right? It's not just diagonal terms, but it has block matrices on the diagonal and 0 submatrices off the diagonal. So we call that block diagonal, okay? So that's the mass matrix. How about the stiffness, okay? And the stiffness matrix K, and this is, of course, the element level stiffness matrix, is given by the following. Okay, it's also comprised of of 8 by 8 blocks. Okay, and so it looks like we call them K11, where I'm putting the superscript on the K's to remind you it's a submatrix. So these are 8 by 8 submatrices. Okay, I'm going to continue writing this in skip for you. You can copy it down or pause the video as needed. Okay, we'll call that equation 10, right? And then for the sake of completeness, I'm actually going to give you the expressions for each of these submatrix blocks. And that's because you're going to be tasked in this class with writing your own FEA code, so you're going to need to use this stiffness matrix. So let me give you those, and again, I'm just going to write them, and it's going to appear rather than have you watch me write everything out. Okay. Okay. Something to note is that the block diagonal sort of transpose component, so the K12 is related to the K21 via a transpose. So K12 is equal to K21 transpose, right? That keeps the stiffness matrix symmetric. Okay, so here are here's the 9 8 by 8 submatrices and their equations that you need to use to compute them. So what's left? I just want to remind you of what these partials represent. Okay, so I'm gonna scroll up and show you just this last equation. We'll explore one of these partials real quick. So here we go. Let's just say recall these equations are written in absolute coordinates. Okay, so what does that mean? That means that i.e. when we write something like n, comma 1, what we mean is the partial of n with respect to x1. Okay? Here's the problem, but our interpolation functions are defined in natural coordinates. Right? We had defined that n, as we've been given, was defined as n as a function of, in this case, xi, eta, and zeta, right? Okay, not n of x1, x2, and x3, right? So the question becomes, how are we gonna handle this? What do we need to do to complete these integrals? We've talked before, we want to use Gauss quadrature. For that, we need to put these integrals in natural coordinates, but it also means we're going to have to do some mapping. So that's where we're headed next. Is now you know what the answer is in terms of integral forms. Now we need to talk about how we actually go about solving those integrals. That's going to be the topic of the next couple lectures.